In this lecture, we will discuss about cyclic group and normal subgroup. So first we start with the cyclic group. Cyclic group. So we define the cyclic group as a group. A group G is called a cyclic group if each element X of the group G can be expressed as X is equal to a raised to the power n for some A belongs to G. And here n we consider as the positive integer. So we consider as the positive integer. So then A is called the generator of group G. Now, so we start the example. So we understand how. So let G is equal to 1 minus 1 iota and minus iota be a group. So the generators of group G is now. So we have the definition x is equal to a raised to the power n. So x, we see that the each element x of a group G. So we obtain each element of the group G. So then this A is called the generator of G. So that means suppose we have the element of group G is 1. We have second element is minus 1. Third element we have iota. And fourth element is minus iota. So now, so these are x. So these are x. So now we take A. A is also the element of G. A also belongs to G. So we take the any elements. So that means which gives us the all the element of the group G. So one cannot give the element I. One cannot give the element minus iota. So one cannot be a generator of G. Minus one cannot give us iota and minus iota. So minus one is also not a generator of G. Now, so we see that. So we have iota. So we take iota as a generator. So what is the power of iota? Gives us 1. So iota raised to the power 4. So iota square equal to minus 1 or minus 1 into minus 1 equal to 1. So now second is minus 1. So again we take the second generator. So minus 1, so I square equal to minus 1. Now third iota raised to the power 1 and minus iota. So iota square equal to minus 1 into iota. So power is 3. So we see that in this iota work as a generator. So I is the generator. I is the generator who generate all the element of the group G. So the I is the generator. Now we move to the second generator. If second generator is possible in the group G, so yes, second generator is also possible in this group. So we take as 1 minus 1, we take iota and minus iota. So these are we consider as x. Now we choose the second generator. That generator will be the minus iota. We have already said that 1 and minus 1 cannot be a generator because we cannot get the iota and minus iota. So here minus iota raised to the power 4, we can get 1. Similarly, for minus iota raised to the power 2. So iota square equal to minus 1 or minus plus 1. So that power will be 2. And minus iota I square equal to minus 1. So this power will be 3. and we get minus iota means power is 1. So here we see that minus iota is the generator. So minus iota is the generator who generate all the element of the group G. Now, hope you understand. We cannot take the 1 and minus 1 as a generator. So for this example, we can write down as, so for this example, 1 and minus 1 will not a generator, will not a generator. Also, we focus on the powers. Power should be positive integers. All power are positive integer, and we get all the element of the group G. Okay, so we can take another example for understanding the class cyclic group. So let G is equal to 1 omega omega square is also an abelian group. Is a is an abelian group. Above also an abelian group under multiplication. Under multiplication. So can write write all the generators. So the generators. So when we write 1 omega and omega square, we treat it as a x. So these are the element of group G. Now one cannot be a generator for this. That means one also belongs to G. So 1 equal to 1. Yes, it is possible, but 1 cannot give us omega and omega square. So 1 cannot be a generator. Now we start from omega. So omega cube root of unity, we know that. So cube root of unity equal to 1. Omega cube equal to 1. So omega. Now omega raised to the power 1 gives us omega. Now omega raised to the power 2 gives us omega square. So for this particular example, omega is a generator. So omega is a generator. So this is called also the cyclic group. Okay, so cyclic group which gener okay. So second also we take as omega square as a generator. So omega square is also generator. So omega square raised to the power 3, omega q into 1, omega q into omega q. So 1 into 1 equal to 1. Now omega square raised to the power 2. So omega q into 1 into omega. So gives us omega, and omega square raised to the power 1. So here we see that omega square is a generator. Omega square is a generator. So omega square is a generator. So these two groups are the example of a cyclic group. So these two are called cyclic group. A group G is said to be cyclic if each element x of a group G can be expressed as x equal to a raised to the power n. So that group is called a cyclic group. So above two example are the cyclic group. So we can write down as, so both examples. So above both examples are cyclic group. Both examples are cyclic group. Now we move to the important theorem. So we have one theorem. The statement of theorem is each cyclic group is an abelian group. Each cyclic group is an abelian group. Abelian group means follow the commutative property. So first we shall prove this theorem. So when we are going to prove, so we write down, let G be any cyclic group. G be any cyclic group. So and let A be the generator, and let X and Y be two element of group G. So then by definition of cyclic group, we write down as x equal to a raised to the power m, and y raised equal to a raised to the power n. So we can add up for some m and n both are belongs to the positive integer. Both are belongs to the positive integer. Now we want to prove this a abelian group. So we take as so we take xy. Xy is equal to, so this can be written as a raised to the power m into a raised to the power n. So this we can write down as a raised to the power m plus n. So a raised to the power m plus n. So this can be written as a raised to the power n plus m. Okay. So we can write down as m plus n is equal to n plus m. So that way we can use the commutative property under addition. A plus b equal to b plus a. So this can be written as a raised to the power n into a raised to the power m. So a raised to the power n equal to y and a raised to the power m equal to x. So we have x y equal to yx. So x y equal to yx. So this gives us the commutative property. So we can say that G is an abelian group. So G is an abelian group. Okay, because we are solving for class cyclic group. So cyclic group is GB. The cyclic group means G itself a group. So we want to prove that fifth property only, or commutative property for proving the abelian group. Now we move to the next definition, that is the normal subgroup. So very important definition, that is the normal subgroup. Normal subgroup. So we define as let G be any group, G be any group, and H be any subgroup of G. H be any subgroup of G means H itself a group. So then H is called a normal subgroup in G if and only if X inverse belongs to H. For every H belongs to H and X belongs to G. So X be the element of G. X inverse जब X belongs to G or G be a group, so it means that X inverse also belongs to G. It is clear. So we can graphically represent it as, so this is our H, and here we have X inverse. So we can say that this is our H, and here we have the X. So X be the element of G, X inverse be the element of G. This belongs to G, this belongs to G, and H belongs to H. So X inverse belongs to H. So now for proving this, so we can take an example. So we take the example. So example, popular examples we can take. So let G is equal to 1 minus 1 iota and minus iota. So be a group, and H is equal to 1 and minus 1. Be also a group. Be also a group. So H is a subgroup of G, and H is a subgroup of G. So then we see that X inverse. So X inverse. So this equal to, we can write down as, so X is the element of group G, H be the element of H. So now we take as X equal to 1. So when we consider, so here we take X is equal to 1. So when we take as 1 and H also take as 1. So H we also consider as 1. So X inverse. So the when G be a group under multiplication, inverse also exists in this. So the inverse of 1 is obviously 1. The inverse of 1 is also 1. So X inverse. So this equal to 1 or 1 belongs to H. So we can say that X, H, X inverse belongs to H. Similarly, now we talk about the second element. So suppose we are considering X equal to 1 or H is equal to minus 1. So we take X as it is and H equal to minus 1. So we can write down 1 H minus 1 inverse of X, that means 1 is 1. So this gives us minus 1 or minus 1, which also belongs to H. So this H is said to be a normal subgroup of G. Now we take for all elements. So that means now we consider other element also, because this is possible for other element or not. So now when we consider X is equal to iota and H is equal to minus 1. So we can see that iota and H is equal to minus 1. And what is the inverse of iota? Inverse of iota is minus iota. Inverse of iota is minus iota. So iota square equal to minus 1. So iota square equal to minus 1. So minus minus plus or minus. So this gives us minus 1. Minus 1 is also belongs to H. Okay, so we remember, so we make a composition table. So for calculating the inverse, 1 minus 1 iota minus iota, 1 minus 1 iota and minus iota. So 1 minus 1, when we do the product, minus, so this can be minus 1 y square minus 1 and minus iota, and here is iota, and here is iota minus iota. Iota square equal to minus 1, or this gives us plus 1. So this is minus 1 and this is iota. Iota square equal to minus 1 means plus 1, and this gives us minus 1. So when we take the inverse, so we see the identity elements. We circle the identity elements. So identity elements, so we see the images of each element through our identity element is, so that is the inverse. So directly we write down the inverse of these. Okay, so image of 1 is 1, so inverse of 1 is 1. Image of minus 1 is minus 1. So inverse of minus 1 is minus 1. Image of iota is minus iota. So iota inverse is minus iota. And image of minus iota. So minus iota inverse is iota. Okay. So all these are also belongs to G. Now similarly, you can check for when we put x equal to minus iota, h is equal to minus 1. So we can write down as minus iota into minus 1, or minus iota inverse is iota. So this also gives us minus 1. So we see that when we take any element of group G, so we apply this x, h, x inverse, so gives us the element of h. So hence h is equal to 1 minus 1 is a normal subgroup of G. So H is called normal. So H, this H means minus 1 or minus 1 is called a normal subgroup of G. Is called a normal subgroup of G. Is called a normal subgroup of G. Now we move to the next theorem. So this is also an important theorem related to normal subgroup. So every subgroup, so statement of this theorem is every subgroup of an abelian group is normal. Every subgroup of an abelian group is normal. So we are proving this theorem. So let G be any abelian group. Every subgroup of an abelian group. So first we take the abelian group. G be any abelian group. G be any abelian group. And H be any subgroup. As per statement, we write down subgroup of G. So then for every X belongs to G. X be any element which belongs to G, and for every H belongs to H, so we take as X H X inverse. X H X inverse is equal to, so we can write down as, because G is abelian. So G is abelian. H belongs to H, so H also belongs to G because H is the subgroup of G. So this X H. So by using the abelian condition, we can write down as H into X. X H. So X H we can write down as HX. So here G is, because G is abelian. So G is abelian group. So abelian group means satisfy the commutative property also. So here we use the commutative property. Okay. So we can write down as this equal to X into X inverse. X into X inverse is identity. So means X into X inverse equal to X inverse into X equal to E by the definition of inverse. So this HE, this HE is equal to H by the definition of identity. HE equal to EH equal to H. So by the definition of identity. Or this H we have considered as belongs to H. So this H belongs to H. So X H X inverse is equal to H. So X H X inverse belongs to H. So then this is the normal subgroup. So every subgroup of an abelian group is a normal. So we can say that. So thus X belongs to G, H belongs to H, implies that X, H, X inverse belongs to H. So hence H is normal subgroup in G.